All right, in this next section, 7.5, method of partial fractions, this is an extremely important algebraic technique. It's not really a calculus technique. We use this algebraic technique. You may have done this and have heard it called partial fractions in reference to rational expressions. You would have done this probably in an Algebra 2 or pre-calculus class. In this context, we are meaning it to be used in conjunction with integration, but really it's an algebraic operation or algorithm. It's an algorithm that we would apply to a rational expression or something that can be thought as a rational expression. Okay, so let's give a quick overview of this. A rational function or any rational expression is expressed as the quotient, the fraction of two polynomials. So we're told that P and Q are polynomials. If the degree of the bottom polynomial, so Q, is larger than the degree of the top, then it is a proper rational function. Much like if we have 4/3, that's improper. It's an improper fraction, but 1/2 is proper. Same idea, but in this case, an improper rational function would be something like, let's say, x cubed minus x over x squared plus 1. Here, the degree in the numerator is 3, the degree in the denominator is 2, so the degree is higher here, so this is considered an improper rational expression. Partial fractions works when we have proper rational expressions or functions. Okay, so the basic idea for partial fractions decomposition is you are given an integral of some expression, and that expression either literally is a rational expression, or it can be maybe under a change of variables or substitution be made into a rational expression. So if you have a rational expression, and we're just going to assume that it's proper, that the degree of the bottom polynomial is larger than the top. So in this case, this is x to the 0th, so this is a 0 degree polynomial, and the bottom we've got a quadratic or a second degree. So this checks out, it's proper. So what we're going to do is factor the denominator. Okay. Now there is the fundamental theorem of algebra that tells us so really there's this there's a split here. So polynomial. So given a polynomial, if you are working with real numbers, it's slightly different than what happens if you work with complex numbers. So with real numbers, the conclusion here would be every polynomial, let's just say factorable, so factorable into linear factors, linear or irreducible quadratic factors. But if you are working with the complex numbers, in other words, you are allowing I, right? You are considering I to be part of your number system here. Then every polynomial is factorable into linear factors. So that's really the irreducibility of certain quadratics. That is what prompted the creation of the complex numbers. Or at least it is a motivation for it, justification for it. For instance, things like x squared plus 1, this is not reducible if you're only allowing real numbers. This doesn't factor. So this would be an example of something that is an irreducible quadratic. But if we allow complex roots, then this does factor into x plus I and x minus I. And you could FOIL this out and check. So again, I squared is equal to -1. So if we FOIL this out, we have x squared minus ix plus ix negative I squared. So these linear terms cancel. We have x squared negative -1. So x squared plus 1. So that checks out. Okay. So we are going to work primarily with real numbers, although we will see I from time to time. So we will actually work with I a little bit, but really this is what we want to think about here. We're either getting linear things or irreducible quadratic factors. Okay, so here's a case where we actually are able to get linear factors. And then what's going to happen here is we are going to essentially do the reverse of a common denominator. So normally when you add things together, like let's think regular old fractions here for a moment. If we take the fraction 3/4 and we want to add it to, let's say, 2/7, what you'd have to do is find the lowest common denominator, or not lowest common denominator, but some common denominator. And an easy way to obtain a common denominator without thinking about it is just to multiply each fraction by the other fraction's denominator over itself. So this fraction, 3/4, gets multiplied by the other fraction's denominator over itself. That will automatically create a common denominator. It just might not be the lowest common denominator. Okay, so here we end up getting 28, of course, and here we have 21 plus 8. So we have 29/28. So our goal here for partial fractions decomposition is, instead of starting with the sum and combining them to create one fraction, we are going to go the opposite direction. We're going to start with a single rational expression, and we are going to figure out how to rip it apart into two simpler fractions. So if we were to do this, to go backwards, what we might do is first begin by factoring the denominator. Well, 28 is 4 times 7. So then I should be able to write 29 over 28 as some number over 4 plus some number over 7. And then working with these two things with the equality between them, we can solve for A and B actually. So it's really like the reverse of adding two fractions together. And that's precisely why we say this one rational expression should be able to be written as something over those factors. There's lots of different ways to determine A and B, different techniques we'll explore, but the next step that always happens is if we can clear all these fractions by multiplying by this entire denominator. If we multiply everything by that, so this term gets an x minus 2, x minus 5, and this term gets an x minus 2 times an x minus 5. So does this term, x minus 2 times x minus 5. Well, here, the x minus 2's and x minus 5's cancel, so we're left over with just 1 on the right-hand side. And here, what's in common cancels. The commonalities go away. And then we are left over with a times x minus 5 and b times x minus 2. From here, we can solve. Okay, so Yeah, we can go through all of this. I would like to go through it in an example. That's what we'll do next. But really, the last thing that we want to talk about in this introduction is essentially, no matter what rational expression we start with, we are going to fall into one of these four categories. We either have something like here, distinct linear factors. So distinct because the factor here is x minus 2, the factor here is x minus 5, and they're different. But what if you had the integral of, let's say, 1 over x minus 2 cubed times x minus 5? Then this x minus 5, this one would be considered a distinct linear factor. But x minus 2 would be considered a repeated linear factor. It's repeated 3 times. And then another option here is these irreducible quadratic factors. So this might be something like, let's say we've got 3x minus 1, and then downstairs we have, let's say, x squared plus 4 x minus 2 dx, something like that. Here, this x squared plus 4 is an irreducible quadratic factor. And here we've got a distinct linear factor. Now, if we made this squared or raised to some power, then this would be a repeated irreducible quadratic factor. So really, the things you need to know are, given some factor in the bottom, is it a first-degree polynomial or is it a second-degree polynomial? If it's a second-degree polynomial, are you sure it doesn't factor further in the real numbers? Remember that if you are ever unsure if something factors further in the real numbers, you can use, we all remember this, the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And this is if we have something starting off with ax squared plus bx plus c equals 0. This would give you the roots of the polynomial. Remember that this quantity on the inside of the square root is special. It's called the discriminant. I'm going to call this d for discriminant. So let d equal b squared minus 4ac. If d is greater than 0, then there are 2 factors, or 2 solutions. If d equals 0, then this is a repeated factors, or repeated solutions. 2. Just 2 exactly. And if d is less than 0, then there are 2 complex factors, or 2 complex solutions. So this d greater than 0, this would be distinct linear factors. If we have d equals 0, then this would be repeated linear factors. And if d is less than 0, we would have an irreducible quadratic factors. Okay. With that being said, let's figure out how to handle each case.